we will whatever we have been discussing on this index notation or tensor notation will continue. So you can see the shared screen.
Yes, sir. We can see, sir.
Okay, okay. Okay, so let us begin. So let us start from a different point. So suppose if I have a coordinate system, okay, so let me say that there is a unit vector in this direction, which I will call it as E1. And there is a unit vector in this direction, which I will call it as E2. And there is a unit vector in this direction, which I will call it as E3. Okay, so for this three-dimensional space, this E1, or let me say EI, okay, so we have said that if I write one free index like that, so I don't have to write like this, I simply say EI. So this is a vector. Okay, so a unit vector. But then there is some kind of a confusion here with the notation. Each one is a vector. E1 is a vector, E2 is a vector, E3 is a vector. So how should I write? I should write something like E1I, like that I have to write. So that E1 is a vector, E2 is a vector, and so on. Right? Now, supposing if I ask a question, suppose if I take EI, so let us now write them as vectors, EI dot EJ. Okay, what will this be equal to? EI dot EJ will be equal to what?
0, sir.
Will it be 0 always? Because
Yes,
I
yes.
don't know. J and I have not defined.
Yeah.
Delta is
That will be equal to delta IJ. So this is what chronicle delta, it's a second rank tensor. There are two free indices. So this is, so the dot product of any two orthogonal vectors, if you have a set of orthogonal vectors, then their dot product is given by this. This is not necessarily a case with 3 dimension. If you have n vectors also, this is what is the dot product of any two vectors. This is something which we know. There is nothing very unique about this or very new about this. But now let me ask the following question. Suppose if I take EI vector and dot EJ cross EK. Suppose if I take this, what will that be equal to? So this is the question that I would like to ask. So what do you think is this equal to?
Plebiscita, sir.
Hmm?
Plebiscita, sir.
So do you recognize that this is equal to epsilon ijk? Is it easy to recognize this? So my question is, can you see this?
Yes, sir. Like we'll get a vector, then we have a dot product, so we'll get a scalar quantity.
Okay. So now, for example, you have epsilon 1, 2, 3. What is epsilon 1, 2, 3? 1.
1, sir.
So that means what? E1 dot E2 cross E3. What is E2 cross E3? E2 cross E3 is
E1.
right. So that is
E1.
E1 dot E1. That is equal to 1. Correct? What about epsilon 132? What is the value of epsilon 132?
-1.
Minus. So do you get -1? That is E1 dot E3 cross E2. Correct? That is equal to E1 dot, this is minus E1, right? So that is equal to -1. You follow? So like that, you can verify that. So by definition, if you have orthogonal vectors, you can say that EI dot EJ cross EK by definition is equal to epsilon ij. So the two tensors, the second rank tensor delta ij and third rank tensor epsilon ijk, we can obtain from the orthogonal unit vectors of any coordinate system that you choose. Okay, they should be orthogonal, that's all. Now from here, it is very easy to visualize that if you have, so let us say that you have a vector A and a vector B. Okay, so that is equal to a vector C. Okay, so we can write Ci, that is Ci is equal to epsilon ijk into Aj bk. So here J, K are dummy indices. J and K are dummy indices. So one can define a dot product, a cross product using this epsilon tensor. You follow? Now you can see, suppose you want to write down, let's say I want to write down A dot B cross C. A dot B cross C. How do I write that? That I must write it as AI B cross C I, right? I should be dummy. But then I already know what is B cross C I. That is AI into this is epsilon ijk bj ck. Correct? Epsilon ijk bj ck. What does that mean? So here there is no So I could write this as epsilon ijk ai bj ck. So ijk, all are dummy here. Ijk are dummy. That is fine because there are no free indices. So left hand side is a scalar quantity. A dot b cross c is a scalar quantity. So this is how we can write down is what do you call this, as a vector triple product. Correct? Now we can ask. So let us now try to see if we can understand this epsilon ijk and some properties of this epsilon ijk tensor. So let us say that, so let us remember the definition once. Epsilon ijk is equal to +1 if ijk is equal to cyclic permutations of 1, 2, 3. Cyclic permutations of 1, 2, 3. This is just a notation. Cyclic permutations of 1, 2, 3. That means, what are the cyclic permutations of 1, 2, 3? 1, 2, 3, 3, 1, 2, 2, 3, 1. These are cyclic permutations of 1, 2, 3. And this is equal to -1 if ijk are non-cyclic permutations. Non-cyclic permutations of 1, 2. What are those things? It is easy. You can flip one of them. So let us say 2, 1, 3, 1, 3, 2, and 3, 2, 1. So there are only 6 permutations, 3 here, 3 there. And then of course it is 0 if any two indices are same. So there are, in general, you can expect this to have 27 elements in 3-dimensional space in 3D, but only 6 of them are non-zero. Only 6 are non-zero. That means all other 21 elements are 0. Okay, so good. This is the definition. Now, you can, for example, you ask a question. So let us try to get some results. Okay. So let's say first one, I ask the following question. Suppose I have epsilon ijk multiplied by another epsilon ijk. What will that be equal to? Here, ijk, all the 3 indices are dummy. So what do you think is this? Can you think of epsilon ijk multiplied by epsilon ijk? What is that equal to?
0, sir.
Why? Why is it 0? Now remember, epsilon ijk, since these indices are repeated, I have to sum over all possible i's, all possible j's, all possible k's, and so on, right? But if I, j, k, if any of them are equal, it will be 0. So that means I have to actually sum over only 6 elements, right? I, j, k is 1, 2, 3, 1, 2, 3, or 3, 1, 2, 3, 1, 2, 2, 3, 1, 2, 3, 1, like that. Only those 6 non-zero elements are summed over. But then whatever is the indices here, same indices I have to put there. Is that clear?
Sir, is it 6?
Yes, it should be 6 because whatever, whether it is +1 or -1, whatever is here, it will be. So if this is +1, this is also +1. If this is -1, this is also -1. So what happens if you want to write this, you have to write this as epsilon 1, 2, 3, epsilon 1, 2, 3 plus epsilon, let's say 3, 1, 2, epsilon 3, 1, 2 plus epsilon 2, 3, 1, epsilon 2, 3, 1 plus epsilon 2, 1, 3, epsilon 2, 1, 3 plus epsilon 1, 3, 2, epsilon 1, 3, 2 plus epsilon 3, 2, 1, epsilon 3, 2. Now, if you see, so this is equal to what? The first one is 1 into 1. The second one is also 1 into 1. Plus third one is 1 into 1. Then fourth one onwards, it is -1 into -1. Plus -1 into -1. Plus -1 into -1. So this is also 1. So you will get 6. Correct? So this is, so epsilon ijk, epsilon ijk, if you are asking what is this equal to, this is equal to 6. Okay, so why we did not use other indices? For example, epsilon 1, 1, 1, epsilon 1, 1, 1. Why did we did not use? Because epsilon is 0. If any two indices are repeated, then the epsilon is 0. So even though there are so many other possibilities, only these are the non-zero terms in this summation. Okay, otherwise you have to write 27 terms like this. Since 27 terms, only 6 terms are non-zero, we are writing only those non-zero terms. Okay. Okay, so if you understand this, then we will go to next thing. Suppose now what I do, I will make only one of the indices different. So let's say epsilon ijk and epsilon ijl. Okay, I will make one of the index different. So now tell me, so in this case, this is, all indices are dummy, right? So this is a scalar. And we have got that to be a scalar here, that is 6. Now here, what is this quantity? Ij are dummy, right? Ij are dummy. What about K and L?
Free indices.
K, L are free. So what is the quantity? This quantity is what? It's a tensor of rank 2. Because there are 2 free indices. So it will be a rank 2 tensor. Now what is the tensor? That is what we would be interested in. Now you have to sum over I and j. Correct? So now ij cannot be equal, right? So what are the possible non-zero terms this ij can be there? So ij can be 1, 2, or it can be 2, 1, or it can be 1, 3, or it can be 3, 1, or it can be 2, 3, or 3, 2. Any other possibility? These are the possibilities, right? I and j have to be different. So it is 1, 2, or 2, 1, 1, 2, or 1, 3, or 2, 3. Correct? So I have to sum over these many terms. Now K and L can be anything. K and L can be anything. Just 1 minute. Shrutikanta, you are there?
Yes, sir. Yes, sir.
Okay, I will join in a minute.
Yes, sir. Huh,
Uh,
sir.
I
Hello.
will make you a host and I will come back. Huh?
Yes, sir. Yes, sir.
You can actually stop the video for some time. Okay, so you are able to see this notes, right?
Yes, sir.
So now you have this ij can be like this. That means I must probably write this epsilon ijk and epsilon ijl. This I should write it as epsilon 1 to k, epsilon 1 to l, plus epsilon 21 k, epsilon 21 l, plus epsilon 13 k, epsilon 13 l. These are the 6 terms. So I am writing everything explicitly. 31 k, epsilon 31 l, plus epsilon 23 k, epsilon 23 l, plus epsilon 32 k, epsilon 32 l. Recognize that every other term will be 0. Only these are the terms. But these are the terms which are here. K and L can be anything. So you will still have each one of this. K can be 1 to 3, L can be 1 to 3. But then, since this is 1, 2, if K is 1 or 2, then that will be 0. Similarly, if L is 1 or 2, that will be 0. So when can this term be non-zero? Only when K is equal to L is equal to 3. Correct? Only then this is non-zero. Similarly, what can we say about this? This is also true only if K is equal to L is equal to 3. Correct? What about this? This is also non-zero only if K is equal to L is equal to 2. Whereas this is also non-zero if K is equal to L is equal to 2. And this is also non-zero if K is equal to L is equal to 1. And this is non-zero only if K is equal to L is equal to 1. So from these things, what happens is that whatever is K, L also should be same thing. Correct? But then that means what? K should be same as L. Only then this is non-zero. But then you can see, suppose you take 2 and 3. Epsilon 2 and 3 is -1. And this is also -1. So it will be +1 and +1 only. Correct? So if whenever K equal to L equal to 3, okay, whenever K equal to L equal to 3, I will have, so what can I write this in? What can I write this as?
So it's a scalar.
It cannot be a scalar, right? Because there
And the
are
values, if you choose the K equal to L equal to 3, then you have 1. Like
Sir,
that,
we can use Kronecker delta.
okay. So how do I write it? What kind of chronicle delta is this?
Delta KL, sir.
Correct. So this is just delta KL. This is a second rank tensor, right? So I said this will be a second rank tensor because there are 2 free indices. So this thing is simply delta KL. Because if K is 3, L is 3. If K is 2, L is 2. If K is 1, L is 1. Correct? So is it simply delta KL? Suppose let us say K is equal to L is equal to 3, delta 3, 3. how many terms do I have here? K equal to L equal to 3.
It is 2 times delta KL, sir.
Ah, very nice. So it is 2 times delta K. It is 2 times delta K. So what is it that we have learnt? If two indices are same, ij, and K and L are different, it is 2 times delta K. Okay, is that clear? Then we will try to go one step further. So now we will ask, what is epsilon ijk multiplied by epsilon ilm? So here what are we saying? Only one index is common. So here I is dummy. And how many free indices are there? J, K,
4.
L, M. 4 free indices. So as a result, what happens? This is a tensor of rank 4 tensor. Do you recognize? Because there are 4 free indices. So how many terms will be there in 3 dimensions? It's a rank 4 tensor, so there will be 81 components. That is 3 to the power 4. 81 components in 3 dimensions. Okay. Now how do I? So now you can see whatever is your dummy index, I, will be 1 or 2 or 3. Correct? So let us look at that. So epsilon ijk into epsilon ilm is equal to epsilon 1 jk, epsilon 1 lm plus epsilon 2 jk, epsilon 2 lm plus epsilon 3 jk, epsilon 3 lm. Because whatever is the dummy index, I am expanding that first because I is summed over. So I am writing 1, 2, 3. These are the 3 possible values of I in 3 dimensions, right? Now look at this one. Epsilon 1 is fixed. So J and K can be what? J can be 2, K can be 3. Only then this will be non-zero. Similarly, now LM can be 2, 3, or it can be 3, 2. Correct? So suppose if I fix epsilon 1, 2, 3, then you can have a possibility that it epsilon 1, 2, 3, or you can have a possibility of epsilon 1, 3, 2. Even then that is non-zero, right? It is non-zero. Correct? Plus, you can have a situation plus epsilon 1, 3, 2 into epsilon 1, 2, 3 plus epsilon 1, 3, 2. We can have that situation because see J and K can be 2, 3, 3, 2. So 2, 3, 2, 3, 2, 3, 3, 2, 3, 2, 2, 3. So these are the possibilities, right? So that means it is like epsilon 1, 2, 3 plus epsilon 1, 2, 3 like this. Now, if you look at this term, okay, if you look at this term, you can see that this 2, 3, 2, 3 are 2, 3, 3, 2. That means J is same as L, K is same as M. But if you flip this, that means J is same as M, and k is same as L, then what happens? There will be a minus m because epsilon 1, 2, 3 is plus 1 and epsilon 1, 3, 2 is minus 1. Right? So that is plus 1 and this is minus 1. Correct? So what you can see, plus I'm not writing the other terms. So that means what? We are going to have. So whenever j is same as L and k is same as m, we will have plus 1. Whenever j and m are same and k and L are same, we will have minus 1. Okay. So you can write that using canonical deltas. You can say it is delta j L into delta km. So in that, whenever this happens, it is 1 minus delta jm delta km. Okay, that is j can be equal to L, k can be equal to L. In that case, this will be plus 1. Okay, but remember the 4 free indices are there. So whatever I have written in the bracket is a 4th rank tensor. And whenever j and m are same and k and L are same, it will be one of them is positive, other one is negative. So it will be a minus 1. So I will have a minus sign here. And this is what it is. Okay, so this is an important identity, epsilon ijk and epsilon ilm is equal to delta jl delta km minus delta jm delta kl. Now, let's try to see where this is useful. Suppose, let's say we are interested in an identity like this. So let's say prove that A cross B, A cross B cross C is equal to B dot B times A dot C minus C times A dot B. So this vector identity, I am sure you have seen this. You have proved this in your earlier classes on vectors. Now, how do I write this, or how do I use it in this notation? So we will start with this A cross B cross C. This is a vector quantity, right? So the ith component of this I is equal to epsilon ijk aj into B cross C of k. I can write like that, which is equal to epsilon ijk aj. Now I will write B cross C of k as epsilon k lm, epsilon klm bl cm. Now once I write everything in terms of this notation, I can write this as epsilon ijk epsilon klm aj bl cm. Now notice this ijk or kij doesn't matter because it's only a cyclic commutation. So I can write this as epsilon kij epsilon klm aj bl cm. Now I am going to use the result that we just established. That is product of this epsilon where only k is dummy index and ij and lm. Of course, here, what is free index here? K is summed over, ij is free, lm is summed over. Sorry, j is summed over. So you will get only I, because left hand side only I is the free index, right? So now I'm going to use that result. This can be written as delta IL, delta JM minus delta IM, delta JL into AJ BL CM. Now you can see the first term I equal to L. So wherever L is there, I will put I. Wherever M is there, I will put J. So I have AJ BI and CJ minus wherever M is there, I will put I. Wherever L is there, I will put J. So that means it is AJ BJ CI. So you can see here J is dummy. That means I'm going to write as BI into AJCJ minus CI into AJBJ. What is AJBJ if A is dummy? Is A dot B. Correct? So that is what gives you B vector times A dot C minus C vector times A dot. So you can see that if you know this identity of epsilon ijk, you can solve this kind of problems very easily. Now let me leave this as an exercise. Before this exercise, let me say that we are going to define this operator del in this index notation as simply del I, which actually stands for partial derivative with respect to xi. Okay, but we are going to simply call this as del I. Okay, so now show that del cross a vector A is equal to gradient of divergence of A minus del square A. Gradient of divergence of A minus del square A. So I will leave this as an exercise for you. You can use the same trick as in this. Okay, so that is for you to practice. Now let us look at the final thing here. That is, I'm now going to ask what is epsilon ijk and epsilon LMN. Nothing is dummy here. Nothing is dummy. So this is all are free indices. So that means 6 free indices. Okay, 6 free indices. So this is a rank 6 tensor. Correct? The rank 6 tensor. Now you can ask a question. How do I write this? Suppose, so let us say that if I So let us fix I is equal to 1 and L is equal to 1. Okay, suppose if I fix I is equal to 1, L is equal to 1, then that means I can use previous result, right? I can use previous result. What is the previous result? For this, if I fix this, I have fourth rank tensor, right? So for that, I have delta JL, delta KN, sorry, delta JM, delta KN minus delta JN, delta KM. Okay. Now what happens if I take I is equal to 1 and L is equal to 2? If I take I is equal to 1 and L is equal to 2, then what happens? That means I have epsilon 1 JK and epsilon 2 MN. Correct? So now you can see, so this JK can be as usual, that is 2, 3 or 3, 2. And MN, so this JK can be 2, 3, 2 or 3, 2. And MN can be 1, 3 or 3, 1. Only in that case, we will have non-zero values, right? So that means we are going to have this one as epsilon 1, 2, 3 into epsilon 2, 1, 3. Okay, plus, okay, that is one component. And epsilon 1, 2, 3, epsilon 2, 3, 1. That is one component. Epsilon 3, 2, 1, 3, 2, epsilon 2, 1, 3, and epsilon 1, 3, 2, epsilon 2, 3, 1. These are the components that will be non-zero. So this is 1 and this is minus 1. So totally this will be minus 1. This is 1 and this is minus 1 and 1, 3, 2. Okay, so this is 1. Sorry, this is minus 1 and 2, 1, 3. This is also minus 1. 1, 3, 2. This is minus 1 and 2, 3, 1.
Sir?
Yeah.
Hello, sir?
Yeah,
Sir,
yeah.
in previous thing, epsilon 2, 3, 1 is also 1, no, sir?
Where?
In the second case, epsilon 1, 2, 3 is 1. Epsilon 1, 2, I mean, epsilon 2, 3, 1. That is also 1, no, sir? You put minus 1.
Epsilon 2, 3, 1.
That is also 1, no, sir?
2, 3, 1. Yeah, that is also 1. Correct.
Yes.
So that is 1. And this is minus 1. What about 2, 3, 1? 2, 3, 1 is
1, sir.
yeah,
2, 3, 1.
1. So you can see that this is giving you a minus 1 and this is a plus 1 and this is minus 1. This is plus 1, right? Okay, so these components are giving like this. Okay. Now, so that means what? If you are, so you can see that so you can see that so this can be clubbed in this fashion. Okay, so I want you to just argue that you can write this in the following fashion. Suppose if I have ijk, okay, so I want you to just look at this So this can be written as delta ij, sorry, delta il, delta im, delta in, delta jl, delta jm, delta jn, delta kl, delta km, delta kn as a determinant of this. Okay. So for example, if one of the index is, if the one of the index is same, so let us say I is equal to L, let's say. One of the index is same. So then what happens? This I is equal to L, that means this entire row, this is L, LM, LN, right? So then this determinant will reduce to determinant of only this one. Correct? If I is equal to L, then only this term will be non-zero. These terms will all be zero. So your determinant will simply be delta Jm. That is, for this case, you will have delta Jm, delta Kn minus delta Jn, delta Km. That is what we have seen in the previous result. But in general, if you have all the three components are different, then we will get this. We will get this one, a determinant form like this. Okay, so this is something which we can use in calculations, but you remember that this can be written as you can see. This I is the row index I, and then this LMN are changing the column, whereas here IJK is changing along the rows and L is the column index. So it's not very difficult to remember this one. So this is the most general expression for the product of this epsilon matrices. Okay, so I will stop here and so we can proceed with Professor Kapoor's.
Good morning, Professor Satya.
Good morning, Professor.
How are you?
Fine, thank you.
We'll start after 5 minutes. Let them have some break for 5 minutes.
Yeah. Ritesh?
Yes, sir.
Okay, you are there, right?
Yes, sir. Sir, I had one doubt, sir. Sir, when you went offline, like for 1 minute, 2 minutes, Shritikanta sir was telling about when we interchange. For example, when we permutate this 1, 2, 3, 3 to 1, he's telling that also can be done like fixing one of the indices and interchanging the other two. That is a universal method. For example, if it is epsilon 3 to 1, we want to have that. We can tell -1 if we do even number of changes to bring to that point, or when it is odd number of changes, it should be -1. When even number of changes, it is +1. Like that, he was telling one method, sir.
Yeah.
For example, can you show us some in a 4 dimensions, sir? Like 1, 2, 3, 4. Let's assume. And if we interchange any of the, how to interchange by fixing one thing. Fixing one index means we should fix it throughout the process, or is it for just that one process to reach that point? So that was my question, sir.
See, whatever is the number of indices, the cyclic permutations are, the total number of permutations are fixed, right? N factorial permutations will be there.
Yes.
If you have N indices.
Correct.
So cyclic permutations means you are going to So you write down, draw a circle and put these numbers in some anti-clockwise direction. Okay. And then you say you start from 1, 2, 3, 4, or 2, start from 2 and then follow in the same counterclockwise, clockwise direction, whatever direction you choose, or in whichever direction you have drawn those numbers in the increasing order. So then you follow that direction. You start from 1 or 2, end at 1, or 3 at end at 1, or 4 at end at 1. So you get, these are cyclic permutations.
Correct.
Now to get any other permutation, you have to do some exchange, right? So you have
Yeah.
to add 2 of them. So they all will carry -1.
-1. So this is also universal rule, whatever you are telling.
Yeah, this is any flipping, no? You exchange. Let's say you exchange 1 and 2 or 1 and 4, that will carry a minus sign. And if you exchange twice, it will be +1.
Correct, sir. So my second question is that, does this form a group? This cyclic permutation, does this form a group? Whatever permutation.
Set of all permutations will form a permutation group.
So that should be a generator, no, sir, for all cyclic groups. So what the generator of this thing? The generator for the cyclic group.
I think the generators will depend on the order of the group, but this is not a cyclic group. I think most the permutation.
Permutation group. Yeah, sorry.
It's not a cyclic group. So there can be more than one generators if it is a non-cyclic group. We will discuss that probably when we talk about groups, but right now we can say, I will just say that the set of all permutations will form a group.